Hi there, welcome to Mr. Morgan's Math Help. This is Algebra 1, Unit 3, Lesson 4, called Water Wonderland. All right, so today we are going to be talking about graphs and equations again as functions. We're going to be writing some equations that we figure out from graphs of functions. We're also going to be combining two linear functions today. All right, and so our questions we're talking about are how does function notation connect to a graph? What connections can be made with function notation and a story context, and how do I combine functions graphically and algebraically? This is going to be probably one of our trickier things today as we go through it. A lot of stuff will make sense, but the combining is a little tricky, and there's a couple ways of doing it, and really the teacher's guide just says, guide kids, they might want to do it this way or that way. So if you get stuck, don't feel like you're alone in that. I was too. So here we go. The first thing begins with a little discussion on Allie and Dayne. They work at a water park, and they are required to drain the water at the end of each month for the ride they supervise. So they're going to drain some water. Each uses a pump to remove the water from the small pool at the bottom of the ride. The graph given represents the amount of water in Allie's pool, AX, and Dayne's pool, DX, over time. Okay. Make as many observations as possible with the information given in the graph. So we have a couple graphs here. We can see we have Allie's line is the red one, right? Starting at this point and coming down to here. And we can see also we have Dayne starting here and going there. So a couple observations you can make is, of course, things like they both are decreasing, right? They're both going down. They're starting up here and they go down to here where there's nothing left. We can see, for example, that Allie's looks like she probably starts with a little more water in her pool, and it tends to drain faster because if this is time here, which it says that it gets done faster than Dayne's pool. In terms of numbers and what those mean, I don't know if maybe my graph cut it off. Mine tells me that this point right here is 24 minutes and this point is 22 minutes, just in terms of how long that takes. And it also tells me, I think that over here, we'll see in a minute, that this is 24,000 gallons and Allie's starts at 28,000 gallons. So there's definitely more in Allie's pool. It drains faster. Dayne's pool has less water and drains slower. There's also this point right here where they do seem to be at the same water level because this is measuring the amount of water. And so at this point right there, they have the same amount of water, which is an interesting thing to kind of notice. But eventually, they all become empty. All right. So write an equation to represent the draining of Dayne's pool. What does each part of the equation mean? So Dayne, first of all, figured out the pump he uses drains the water at a rate of 1,000 gallons per minute, and it takes 24 minutes to drain his pool. So from that story, we're supposed to come up with an equation to say, okay, if that's true, then what's an equation that we can use for his pool? Well, a couple things I would say. If the pool is drained at 1,000 gallons per minute and it takes 24 gallons to drain it, or 24 minutes to drain it, that means if we took the rate of 24 and multiplied it by the number of minutes it says it's going to take, that means it starts with 24,000 gallons to begin with, which is what we said back over here. I just kind of jumped ahead of myself. So we know that our y-intercept, so to speak, because this is our y and our x, is at 0, 24,000. Now knowing that, if we know how to make the graph of a line, we know that we can use our rate, which is, is 1,000, it's losing 1,000 gallons per minute. So that's my x per minute there. And we know that our y-intercept is where it starts, and that is going to be at 24,000. So one way to write an equation could be to simply say that d of x is equal to the rate that it drains, negative 1,000x, plus the y-intercept right there. You could also write this, and your teacher might have written it down this way as well, as 24,000 minus 1,000x for d of x. That's the same thing. You're just changing it to start with a positive number in front. Okay? So in terms of, again, what does this mean? This is how much water he started with, and this is the rate at which it's going out of the pool when he drains it. So based on that, can you label the graph shown? Yes, and we've done that already. We have 24,000 there, and we have down over here. It took 24 minutes there. I'm not sure we're at 240, but that's okay. I probably was just circling wrong. So 24 minutes here. Wow, I'm not sure what it's doing. All right, 24. All right, so 24 there. Now, check. What value of x makes sense in this situation? Write the domain of the function that represents the amount of water in Dayne's pool. So for Dayne's pool, in terms of the value for the x, it's going to be, our domain is going to start from here and go all the way to here. So 0 to 24 makes sense for the domain for his pool. Now for the output value, that's going to be your range. That's how much water is in the pool. We can see we're starting at 24,000 and we're going down to 0. So we can write 0, 24,000 for our point. And those are points, so we can put the brackets in because we're starting here, 20 here, and going all the way down to 0. Okay, so we can easily figure out an equation. We can do the domain and the range, and we're good. Now it says, write the equation that represents the draining of Allie's pool. State the domain and range for each function. So for Allie's pool, what's interesting to me when I was looking at this is it didn't actually, unless I missed it somewhere, tell me what her starting value was. Okay, I couldn't see that in here. I just know that that's a point there, and I can see it's 22,000 when she's done, and we knew it went above there. So I'd have to kind of go back in my notes and see what that was. I made a note here of 28,000, so I'm not sure where that came from, honestly, so that's okay. We're going to say that what we know is that for Allie, her pool, it's draining at a different rate, right? It's going down. What that rate is we need to figure out how fast is her pool draining. Well, we know that it has a rate that it's draining at, and then we're going to subtract it from or add to it our value for our y-intercept. Now in Allie's case, we can see that it's starting at 28,000. There, that's its first value. We can see over here, we have a couple points. 28,000, we have 0, 28,000 is 1. And then we have a point here, which is 22 for Allie, 0. So to find a rate of change, I could take the values and subtract them there. 0 minus 28,000. And then 22 minus 0. So we end up with 28,000 over 22. Well, that's exciting. You're thinking, well, I don't know what that is. Well, then just get out a calculator if you're not sure sometimes. That's what they're for. So 28,000 divided by 22 gives me a weird number that doesn't make a lot of sense, actually. So I'm messing something up here, and I'm probably wishing I didn't do any of this here. Let me just skip ahead. Okay. So, again, this is a review of class time anyway, so let's just see what my notes would have said. My notes tell me that Allie's rate is going down by 1,400 gallons per minute in order to get there, which I guess we could figure out by saying if I'm 22 minutes times whatever rate it's going to be, what does that get me up to? We know it's going to get to 2,800. So we're trying to say what is that value of x. So 28 divided by, well, it's still divided by 22. Why is that not working out very nice? I'm not really sure. Oops, divided by 22. Huh, I don't even know. Not going to worry about it because I have other things to do. So our domain for Allie, let's move our domain. Our domain for her is 0, and it's going to go all the way to, oh, maybe that's what it is. Maybe it's 20 right here. That's probably what that is. I'm sorry. That makes a lot more sense. 20 divided by 20. See, now I can read my own handwriting. Divided by 20. Yes, so x equals 1,400. That's our rate, so this was okay. So our rate for Allie is going down negative 1,400. Sorry, it was 20. So our domain is 0 to 20, and our range is going to be from 20, oh, well, actually I would say it's going to go from 0 to 28,000 for Allie. Man, I got a little lost there. This is when I wish I could like edit my video up for you quickly, but I don't have time for that. All right, so when a of x equals d of x, what does this mean? Well, this is going to be the point at which those two lines cross each other. That's the point where the water level is the same and they have the same amount of value of water in there. So the even water mark in essentially. That's what that means. So you could almost think of it like you could take your two equations and set them equal to each other. So you could take Allie's negative 1400x plus 28,000, and you could set that equal to Dayne's negative 1000x plus, what do we say for him, 24,000. And then from there, we could actually put those things together. I could add a 1400x over here, add a 1400x over here. And so now I have 400x on this side. I could subtract 24,000, subtract 24,000, and now I have 4,000. And then I can divide both sides by 400. So I'm left with 40 over 4, or 10 over 1, or simply 10 equals x. So when I look over here, this means that at this point, 10 is where the water values were exactly the same. And if I plug that number back in, it would tell me actually what that value is going to be. So if I plug the number 10 into any one of the equations, it'll give me the y-intercept and tell me at what water level they were when they were both the same. So find a at 5. Well, finding a at 5 means plugging 5 into that equation and solving that. And what does that mean? That means how much water was in the pool 5 minutes after you started draining it. That's all that means. So you're taking that number, you're plugging it in. So you do 5 times negative 1400, multiply that out, and then you add that to your starting value. And when you do that, you come up with 21,000. So that's where that's going to be. The next one, if d of x equals 200, then x equals what? Well, what's that mean? Well, what it's saying here is if I'm at 2,000, or if I have 2,000 gallons left in my pool, what is my x value? How many minutes does it take before I'm sitting at that value? So you're thinking about over here, if I have a number 2,000 somewhere over here, right? If this is 28,000, 2,000 is going to be somewhere around here. So what is that minute value going to be when I reach that point? That's what it's asking you. And if you use the 2,000, put that back in your equation, you find out that, well, x is equal to about 22. That's when that happens, right about there. And finally, when is a of x greater than d of x, and what does this mean? Well, a of x is greater than d of x, well, right here, right? That's where it's greater. So what does it mean there? Well, that means that for about the first 10 minutes, from minute 0 to minute 10, there's more water in pool A than there is in pool D. That's all that means. Okay, so that's what it means there for that one. This month, Allie and Dayne decided to work together by putting both pumps in the pool at the same time to drain their pools and created the equation g of x equals her equation plus his. So essentially, her pump plus his pump working at the same time should create a new equation for how quickly the pool can be drained. They wrote their equation. When they wrote their equation, Allie and Dayne decided they would only need only model the time when the pumps were in the pool, so they didn't have to worry about the short time it took to move the pumps. So what does g of x represent? Well, g of x in this case here is going to represent the sum. It's going to represent the sum of a of x plus, plus d of x, right? The total amount of water that's actually pumped out, because they have to pump it all out. So that's what g of x is going to represent, the whole amount of water, not just this amount and this amount, but now we need to add those together to get an amount way up there, because if we combine them, we're going to have a much larger amount, okay, which is actually something more like 52,000. So if you put both pools together and use the pumps together, what does your graph look like? That's kind of the question, right? If I put both pools together and then stick 2 pumps in them, now what happens to this graph of the water as it drains? What's the rate? And that's what we're going to look at next. So graph g of x on the same axis as a of x and d of x. Okay, so we already said that what we want to do is combine those two amounts. So we know we're going to be at 52. These are 2, 4, 6, 8, 10. So we're going to be starting right about here. I should probably use a different color since that's already going to be a red one there. So we're going to start here, and we know we need to decrease. And that's where we're starting at when we combine the two pools together, and we're going to figure out what that's going to look like. Okay? Now, what it looks like, I don't quite know, but this is what we know so far. So, next question says, write the equation for the function g of x using the graph you created. Well, we didn't make a graph quite yet, did we? Well, how come we didn't make a graph? Well, because I'm not sure what we want to do yet. Well, to do this here, what we should do is we should combine from question 11 those two equations to make an actual g of x. So let's do that. All right, so if I take my a of x, which is 28,000, and I subtract 1,400x, and then I add to it my 24,000 for the d equation minus 1,000x, this is what g of x is going to equal. It's going to equal all those things together. That's my a of x and d of x. So now when I combine that, I have 52,000 minus 2,400x is my new equation for g of x. So that's my equation. That's my rate at which the pool is draining. That's my starting point there. Okay, so if I write this over here one more time, I have 52,000 minus 2,400x is my g of x equation. So if I was to graph that out and figure out, well, what does that mean? I put some values in there. Let's say, for example, we stick a 10 in here. Well, let's do that. 2,400 times 10 is going to be equal to 24,000. And we have it negative, so we add that to 52,000. And we have that equals to, so if I did like a little graph here, at 10, here's my x and my g of x. At 10, the value is going to be 28,000. So here's 10, and 28 is going to be here. So find where 10 and that come together, and I have a line right there. Okay. Now another way of thinking about what that line is if I look here at this point, this is my point of 10, 14,000 for both of those equations. If I'm just adding up the amount of water at this point, if I do 14,000 plus 14,000, what do I come up with? Well, I come up with 28,000, which is this point right here, 10, 28,000. So that's one point on my line. So I have a starting point, I have a middle point. I do need to find out what my ending point is actually going to be. That'd be a good thing to kind of take a look at and see. What that's going to be, again, hard to say. Again, my line's going to look something like this and come down there. And so it should end up being something along those lines. We can see it's probably going to end somewhere between the 20 and 24, which makes sense. So it's interesting, kind of averages those things out. All right, so write the equation for the function using the graph you created. Okay, so we did that already. That's our equation, g of x equals 52,000 minus 2,400x. So that's our equation. Should the algebraic equation of g of x be the same as the algebraic function created from the graph y or y naught? And the answer is, yeah, it should be. It should be because it's saying the same thing. So I'll leave it at that. That's pretty much why. Yay! All right, so moving on to the next one. Use both the graphical and algebraic representation to describe key features of and explain what each feature means, each intercept, domain, range for the situation. Okay, so it's really kind of looking at the information we talked about, on this new one here, what's going to be our domain. Okay, so when you look at here, the domain value is going to be where we started at, which we said was 0, and we're going all the way to somewhere over here. Now, my book tells me that my domain is going to be at 0, and it goes all the way to 65 divided by 3, which is an interesting kind of number. Like, I wonder where they got that from, which is 21.66. And we had said it should be somewhere, we look at our chart here, a little less than 22 based upon just my arrow, my line. So that's the domain there. I'm not sure exactly how they wanted you to figure that one out, but I guess you probably could. You could figure out when it's equal to 0. Well, yeah, you want to find out when this is equal to 0, at what point that's going to be, which is 65 over 3. Anyways, so you could do that. There's probably a way to figure it out, but we'll move on. Our range in this case here is going to be starting at 52,000 and going down to 0. Our whole range is there to there. So we always put the little one first, 0, 52,000. That's our range. Yeah, that's what that is. So is there any increasing? Nope, it's never increasing. It does decrease, but it decreases from where? It decreases from 0 all the way to this number right here, 21.66 or 21.7, however you want to say that. My answer key says 21.7, so that's kind of your idea. That's the decrease value there. Is there a y-intercept? Sure, that's the y-intercept. Is there an x-intercept? Sure, that's the x-intercept right there. That's where that's going to be. Is there a rate of change? Yes, our rate of change is here, negative 2,400, which means that we are losing 2,400 gallons per minute with the pumps working the right way. And again, is it a function? The answer there is yes, because there's only one output for every input. So we're going to say yes there. So we kind of went through a bunch of those questions there. And then 16, explain why adding the two values of y-intercepts together in an ax and dx can be used to find the y-intercept of gx. Well, that's because you're adding two output values at 0, so it's going to add up to equal what g is going to be. You're putting your a output and your d output values together, and that's going to give you the same output, combining them to get your g of x. So can the same thing used to find the x-intercept? No, it's going to be different, and that's because the x-intercept is actually looking at time, and those are different time spots. So you can't compare the time things. The water works because of water, it's the same amount of water, but time, it's not going to work for time. We'll leave it at that. Okay, so we're going to pause here and let you start your homework. Some of the things are going to make sense from our lesson, and some of them are simply not. So when we get there, I will do a little kind of recap on some things because the lesson didn't make it clear to me for what to do in a couple things. So maybe it did for you. I don't know. So pause here, work on your homework. You get stuck, then come back, press play, and let's see how you're doing. All right, welcome back. Here we go. Taking a look today at your homework for lesson 4. For these first sets here, you're just supposed to solve the equation. There's not much to cover here, so really I'll do a couple, but I don't really need to. This is from, honestly, like 6th, 7th grade math. So to get x by itself, we divide both sides by 3, and x is going to be equal to 27, right? So we're just solving for different equations. That's all we're being asked to do. If I did this one here, I could first add 12 to this side, and that becomes 42, which equals what I have left, negative 6. I still need the n by itself, so I'll divide negative 6 by both sides, and n is going to equal negative 8. And that's, negative 7. Sorry about that. Negative 7, that's all there is to that. So I'm not going to do these ones here. These are things you should be able to do on your own as a algebra kiddo. Number 7. The graph models potential business growth for two companies. Both companies are just getting started. Company A expects growth to increase at an increasing rate, while B expects a constant rate. So B is looking at constant, and A is expecting a little more increasing rate overall. So we can see the two graphs when we look at these, right? These charts. So B has this constant rate just moving on up, that's B, whereas A says we just think what's going to happen is it's going to suddenly start to increase and then get higher later on. So first question says, estimate when, if ever, will the companies have the same profit? Well, the same profit's going to be based upon, here's our dollar amount, this is the money here. We can see zeros there. So what point do they have the same profit? Well, that's going to happen when the graphs intersect each other, which occurs right about there. So essentially, where is that happening at? Well, it seems to be happening Well, we're looking here a little bit after year 11, right? Somewhere around year 11, it looks like they're going to have the same amount of profit. So for the first 11 years, or at least 10 years for sure, Company B seems to be doing better, aren't they? Right? Company B is doing well, and they're above Company A for all this time. They're making more money, they're making more money until we get to here, and then they flip, don't they? Now, how much money are they making at that point? We could look here and say, well, what is that value? It comes across there, so somewhere here. They're probably making about $1,400 profit by year 11. So which company has the higher profits at the end of the comparison? Well, the comparison's interesting because it just kind of stops. This one runs out of room. We can't see where it's going. We can only imagine it's going higher and higher. And this one is constant and steady. So overall, at the end period, which one has the higher value? We would definitely say Company A is doing better, which makes sense because they're expecting the increasing rate, or a little bit more like we talked before as an exponential type of growth model. 1L, sorry. What are the y-intercepts and what do these mean in terms of making money? Well, our y-intercepts are down here this time. Notice that they are both below the 0. That's because they're starting the company out, but they're starting at a place where they don't actually, when you start a business, you don't start with money. You have to have startup costs. You have to buy things to get your business going. So at year 0, when they're beginning, we can see that they both owe some money, okay? Company B is at about negative $500, and Company A is at about negative $1,000. So they're not making any money at the start because they had just begun, and they probably have to pay some things back for getting the business up and going. That's a normal kind of a startup cost. When does Company A start making money? Well, again, making money means you've started, you get above the 0 line. So you don't make any money until you cross that line. So Company A doesn't start making any money until year 10. That's when they finally start making some profits at that point. So if you're in Company A, you're working really hard for 10 years, but nothing's going to happen until then. And then suddenly it's going to take off. Company B is going to feel like we're making money, but eventually A is going to make a lot more. Okay? So 2 different business models there. Number 8, graph the explicit function h of t equals 2t minus 5 and find the indicated values. Okay, so to graph this one here, and this is one we'll go ahead and do, we're gonna graph it out, and the way I'm gonna graph it out in this case is we're actually just gonna make ourselves a little table like we've done before. So we're gonna say t and h of t, and we're gonna draw our t chart like so. All right, and I'm just gonna drop in some numbers. We're gonna put in a 0 and a 1 and a 2 and a 3 and a 4. And then we're going to plug them into here. So we think about 2 times 0 minus 5 equals negative 5. Got it. A 2 times 1 minus 5 is 2 minus 5 is a negative 3. Okay? All right, and we know that our rate of change is 2, so we're just adding 2 every time. So I can continue to plug it in, or I can just add 2. I'm just going to add 2 so I can move along a little faster. And now I have some points that I can plot. So I can plot 0, negative 5 for that one. 1, negative 3 there. 2, negative 1. 3, 1. And 4, 3. All right. So now I have my line, and I can draw my line there. So now I've graphed it like so. Okay, so now we've graphed it. Graphed it by making a little t-chart. It's one way of doing it, okay? Another way could have been to simply say this is my y-intercept, negative 5, and then I have my slope of 2, and I could have gone up 2 over 1, up 2 over 1, and then made myself those same points. Different way of going about it. Now, when I look at the next thing, they said, oh, well, now let's find some values. Let's do h at negative 4, which simply means we're going to take our equation, we're going to put a negative 4 instead of the t, and we're going to solve that. So we have negative 8 minus 5 equals a negative 13. That's all they're wanting to do. This one, h of t equals 23, meaning I have 2 times t minus 5, is going to be equal this time to 23. And we're trying to figure out what value of t makes that true. So we'd add 5 to this side. So 2t is equal to 28. We'll divide both sides by 2. And so t is equal to 14. The next one, we're going to say that t is 13. So 2 times 13 minus 5 is 26. Minus 5 is 21. Okay, so when h of 13 goes into play, the answer is 21. And finally, our last one, when is it equal to negative 33? Same idea. 2t minus 5 equals negative 33. We'll add 5 to both sides. So 2t is equal to 28. We divide both sides by 2. Oops, negative 28. And t is equal to negative 14. Okay, so we've taken an equation. We've made it a graph. We've also made it a table. And we've used that equation to find other points as well that may not necessarily be on our graph. Okay, all right, that is number 8. Now, when you get to number 9, it gets a little weird, right? You're like, oh no, it's an exponential one. That's okay. Looking at it exponentially, what I would recommend doing is, again, finding some points that you can see and using those points to see if you can then create a table. Here's my x, here's my y. At 0, we know we're at 1. At 1, we're at 1, 2, 3. And at 2, we're at 9. From that, then I can maybe see, can I write an equation to see what's happening? Sure. 1 to 3 is multiplying by 3, multiplying by 3. We have a starting point of 0. So that tells me, in terms of my equations, I have f of x, or in this case, I guess really g of x. G of x is equal to my first point, which is 1, times what I'm doing, 3, to the x power. Okay? And it's just the x power because we're starting at 0. So really I could say g of x equals 3 to the x power. Now that's my explicit rule. So I'm a little bit ahead of myself in terms of writing this down, but that helps me know what I'm going to do with the other ones. So now I can use this information for these guys. So what do I do when it's 2? Well, that's 3 squared, which equals 9. How about what do I get to make it equal to 3? So you're really saying 3 to what power equals 3? Well, that's going to be 3 to the first power. So x is going to equal 1. And what happens when it's 0? 3 to the 0 power equals 1. So that's all they're asking you to do. And I say all, but you know, it is sometimes a little tricky to go back and say, I have to turn this into one of those explicit equations using the rules to figure that out. So kind of make a little note card for yourself maybe for how to solve or how to figure out explicit equations. It does come in handy. All right, on the next one, number 10, again, we have another chart. At least it's linear for us. That's nice. And a couple ways of approaching it, right? You could do a t-chart if you wanted to. You could look and see that I have a y-intercept there. And with that, I can see, do I have any other values where I have a point? Here's a point there. So I can see I'm going down 1, 2, 3, and over 1. So I can see that my rate of change is down 3 and over 1. And I have a y-intercept value of 5, 6, 7. So I could say that r of x equals, write it nicely I guess, r of x equals negative 3x plus 7. That's one way of looking at it if I was to just look at the graph. If I was to take the points along the line here, okay, and I have lots of points to choose from, I could do a point at 0 and 1 and 2. And at 0 again, we are at 7. At 1, we're at 4. And 2, we're at 1. So I can see that we are doing what? We're subtracting 3. So that means that my r of x is equal to, in this case here, we have our rate, negative 3 times x, and then our first value here, plus 7. Okay, so I can use the t-chart too. After that, then you're going to plug things in. Okay, I'm going to plug them into my equation. So negative 3 times a negative 1 plus a 7 becomes a 4 plus 7, which equals, in our case here, 3 plus 7, which equals 10. All right, when does it equal 4? Well, that's negative 3 x, right, plus 7, and we're going to make that equal to 4. So if I subtract 7, and I put negative 3 equals negative 3. Negative 3 equals negative 3. Divide both sides by negative 3, and x equals 1. So we have a 1 there, a 10 there. How about when r is 2? Okay, so same idea. We have negative 3 times 2 plus 7, negative 6 plus 7, which equals a positive 1. And we've already written our rule for explicit rule here, and you can use this guy right there. Okay, so those ones aren't too bad, right? That's not too bad. Now, when I got to this point, I went, oh, what is it wanting me to do? And honestly, it took me a little bit to kind of play with to figure out what exactly it wanted me to do. And I don't have a great answer for you. I have a couple ways of approaching it, but not a fun way. So this is probably one you're going to want to just double check with your teacher on to see what do they want you to do to draw this new function on the grid by adding the two different functions. Because you have to come up with an equation for both functions as one way of looking at it, or figure out if you have points that you can use to figure out kind of what's in the middle, so to speak. All right, so so for this first one, again, you have a point here and you have a point there. So this is going to be at 1, 2, 3, 4. So at f of 4, it equals 4. And at, was this g? Yeah. And g at 4, it equals 0. So we have a point we can use. Any more points along the way? Here's a point here and a point here. So f of 2, negative 4. F of negative 2 is equal to 2. And g of negative 2 is equal to 1. So we're getting some points along the way here to help us kind of figure out what it might be when you add those things up. Okay, so it's one way of thinking about it. It's like you're adding up those equations like we did with the pool. So if you do it like that, then you're thinking, okay, now I have two values, and if I want to figure out what the h of x is going to be, the h of x, h of 4, I need to find out what that rate of change is going to be. So you're kind of taking the average of the two, essentially. So you have a 0 minus 4 divided by a, 1 minus 2. So you have a negative 4 and a negative 2. So you're at a positive 2. So at least we have in a sense, a slope or rate of change for our new line. The question is, where is that going to start at? That's a great question. I'm not really sure. So I went about it this way. I went ahead and said, let's see if I can find an equation for f of x. So for f of x, let me get an eraser here. Oops, I guess my eraser only stays on while I keep it going. Okay, so for f of x, I know that it went through this point, and I can see it's going this way, and we're going 1, 1 like this. So for me, f of x is going to be equal to my rate of change is going to be a negative 1 over 1, or negative x, and my y-intercept is 0, so that's simply what it is, negative x. For g of x, I saw that I had a point here, that's my y-intercept, and I'm going up 1 and over 2, up 1 over 2. So I can see that my rate of change is 1 over 2x, and my y-intercept is 2. So now when I add those together to get my h of x, what I came up with is that a negative 1 plus a half is a negative 1/2 x, and then 0 plus 2 is 2. So now from this equation, what I did is I said, let's make an xy table, and let's plug some numbers in there to see what we come up with. So if I do negative 1, 0, and 1, negative 1 becomes positive half plus 2 is 2.5. 0 becomes nothing, and a 2. And again, what I can see is what? I am decreasing by a half. So this one then also becomes 1.5. Now from that, then I went ahead, I had some points here. Now I can plot this. At 1, I was at 2, 1, 2.5. At 0, I'm at 2, 1, 2. And at 1, I'm at 1.5, which is, wait, nope, sorry, I did that 2 wrong. Sorry about that. There's 2. And then I'm at 1.5. So this became my 3 points for that line there. So my new function is going to look more like that. And that's how that one's going to look. Okay, that's my new function for h of x. Does that work? Yeah, it works for the most part. But again, this was a weird question. I'm not sure exactly what they want you to do. Most of it was kind of like, just kind of guess and figure it out. So not my favorite. When I got to this one, I felt the same way. I don't really, it's just, again, not my favorite. The numbers are not nice to work with. So it's tough. If I make an equation here, like this one's not too bad, right? I can say I have a point there. I can see I'm going up 1 over 1. So for a of x, okay, no problem. I can see I'm going, just my slope is 1, and my y-intercept is at 1, 2, so plus 2. But for the b of x, there wasn't a nice way to do this one here. I don't really have a y-intercept that's easy to tell. I can see that I am moving down 1, well, I can't really even tell that. I need to find a point. Where's a point at? There's a point here. So here to here. I'm going down 1, 2, and over 1, 2, 3, 1, 2, 3, 4, 5. So I know my rate of change is negative 2 over 5x, but I don't really have a way of figuring out quickly or easily what my y-intercept is going to be. So this one I got a little stuck on. So I'm going to leave it at that, because if I'm a little stuck on it, then maybe you know how to do it, which is great. Maybe you don't, and that's okay too. But it becomes one, just check with your teacher and say, what would you recommend? What's the easiest way to go about this? Because I'm not sure exactly what they're trying to get out of this question, honestly. Okay, so on the next one, moving on, number 14, where does f of x equal g of x? These ones are a little more make sense for the lesson. Where do they equal each other at? They equal each other right there. And in that case, we are at this point, which is 2, and we're at 5. So they equal each other, 2, 5. What is f of 4 plus g of 4? Well, to do that, we look at f of 4, which is, here's my 4 line. And there's a point for f of 4, which is at 5, 6, 7. And g of 4 is here at 6. So really you're saying, here's 7, here's 6, and what do they equal? 13. So that's what that is, okay? How about g at negative 2? Well, negative 2 is over here. So here is 0, 1, 2, and these are our spots. So g at negative 2 is 1, 2, is 3. And minus f of minus 2, which is 1, and that's going to equal a whole 2-ish. It's not exact because those aren't quite on the line, so it's kind of close to 2. So I kind of said 2-ish. All right, so if I erase my things, you'll see those aren't on the line. Yep, you're absolutely right. They're not on the line. It's close. But for what we're doing, it's about 2-ish. If you wanted to say 1.8-ish, fine. All right, state the interval where g of x is greater than f of x. So where is g of x larger than f of x? Well, that's going to be right through here, all the way to that point. Okay, so what is that interval? Well, that interval means it's going to be everywhere from negative infinity, because it's all the way that way, it's always bigger, all the way to this point right here, which happens to be at 2. Okay, for these last ones here, what they want you to do is define the domain and the range and decide if it is increasing or decreasing. That's it. Okay, so I'll do a couple of these, but these ones I think you're getting the hang of here. So the first one, we have a point. We can see we're at negative 1, 2. We're at negative 5, 5. We actually have a point there. We have a point over here for our lowest value. We can see we are at 2, negative 6. So our domain are the x values from here, right, all the way to here. So our domain is going to be, in this case here, -5 all the way to +2. And we have points, so we'll leave it there. Although actually, I colored in my point. I don't actually have a point, I have an open circle, right? So because I have an open circle, this is going to be a curvy line like so, regular parentheses. My range is going to be anywhere from this spot here all the way up to that spot there. So I will do myself another little curvy line, because it's an open circle, -6, all the way up to a closed bracket for a +5 is my range. This one seems to be going down, so we're going to say that it is decreasing. Okay, our next one here, we have a couple back-to-back ones. 15 and 16 are both ones that have kind of some curving one, right? So exponential growth. So for our domain, our x values here, we can see that our domain is going all the way here to -infinity. That's great. But we can see it's going to stop right about here, right? So where's it stopping at? Well, looks like it's stopping at, this is +4. So we're going to say it's stopping at 4. And because it's an open circle, not a point, we'll make that a closed open bracket like this, or parentheses. For our range, we can see that we're right here at about a -1, but maybe not quite touching, all the way down to a -6. So our range is going to be a -6 to a -1. And again, because we read things kind of this direction, left to right, we can see that this is a decreasing equation there. I'll let you do number 16 on your own, same kind of idea. And we have some infinity things, and you can decide which way it's going, increasing or decreasing. So domain, range, and decrease or increase, you decide. And 17, same idea. Domain, range, increase, you decide. 18, same idea. Okay, I guess back up here, recognize here that what do we have? We have some points. So because we have points, make sure you use those brackets to close things in. Over here, we don't have any points, right? It's just kind of going on and on and on. So when you use your domain and range, use the parentheses like so. And then number 19, I think we only have a couple more to kind of look at there. We can see we have a point starting on one side, but not a point on the other. So in terms of this one, for our domain, our range, increase or decrease, our domain is going to start here at -5, and it's going to go all the way, looks like, to infinity, right? But because I have a point, I would do a point -5, and I'm going to say it's going to go all the way to infinity with a parentheses. My range, I'm starting about here. Again, it's a point. I can estimate that it's somewhere between 0 and 1. So if I said 0.5, no one's going to cry about that. If I said a half, that's okay too. Half works as well. And it's going to be going all the way to where? All the way to infinity. And this one is also moving that way, so it is increasing. Okay. This one in this case, right? Interesting just in terms of like, it looks like it is, because of the arrow, you might be tempted to think that it is decreasing, but remember we read things in this direction. So as you go this direction, what's happening with that line? It's going up. Yeah, it might start way over there, but it's moving that direction. So keep in mind, this is actually an increasing graph for us, okay? Increasing function. We do have a point, so we're going to use some of these for that point. This is not a point, so we'll use anything where that one would be like that. So keep that in mind as you look at 21. 22, these are all open-ended, right? No points. We're going to have parentheses. We can see we're going up into positive infinity over here, positive infinity over there. It's going to be great fun as it kind of goes along. And so, yeah, but this one is moving left to right. It's going that way. So we're going to say it's probably decreasing. Okay, so there's some helpful tips for today. Hope that gets you going a little bit, and we will see you next time.